now it's going to be smooth sailing. So we are back on this problem looking at number 4. Okay, so the integral from 0 to 4 of 2x minus x squared over 4 dx, when we integrate here, this is going to be, okay, so this is going to be 2x squared over 2 minus x to the third over 12, and we're going to evaluate that between 0 and 4. Does everybody agree with my integration? You know where the 12 came from? Because it's add 1 to the exponent, put it over it, 3 times 4 is 12. Okay, and so then this is going to be 4 squared minus 4 cubed over 12, which is 16 minus 4 cubed divided by 12, which is 5 1/3, or 16 thirds. And so 16 minus 16 thirds is 32 thirds. Okay? And so that is the moment about the origin. Then you have to get the mass, and then you have to get then you divide those two to get your center. So each one of these problems is 3 opportunities for success. Okay, so then now we're going to get the mass. The mass is a little easier. It's the integral from a to b of the density with respect to x. And so in this case, it's going to be the integral from 0 to 4, and then it's 2 minus x over 4 dx. And so that's going to be equal to 2x minus x squared over 8 evaluated between 0 and 4. And so then this is, make sure I did that good, right? Okay, and so this will be 8, when I plug 4 in, it'll be 8 minus 4 squared is 16 divided by 8, which is 2. So I'll get 6. And that is the mass. And then finally, to get the center of mass, where you should place it so that it balances, you do the moment about the origin divided by the mass. So that's going to be 32 thirds divided by 6, which is 32 thirds times 1 over 6, which is, let's see, we can reduce this. So 2 goes in there 3 times, goes in there 16 times. So 16/9 is the location that you should place the fulcrum so that the rod is balanced. All right? So that's fun, right? But that's not reality, because most of the time you're in more than one dimension, right? So what do you do if you are in 2 dimensions? In 3 dimensions, you wait till Cal 3. But in 2 dimensions, we can kind of handle what we do is we just imagine. So here, this blue circle here, this blue is like, think of this as a plate, some sort of plate cut into thin strips. So we're going to just take one strip and we're going to treat it like the rod, and then we're going to sum them all up, right? So we're going to have like all these little strips. So you can actually have your strip going along the, a vertical strip or a horizontal strip, depending on which is easier to integrate. It's up to you, depending on the situation. But it says what we want to do is think about the moment exerted by a typical strip about each axis is the moment its mass would exert if concentrated at the strip's center of mass, and we're going to call the strip's center, so not the center of mass of the whole plate, but just the center of mass of this little strip, or kind of like this little rod. We call it x tilde y tilde. So that's a little tilde, a little curly guy. And so that's different than x bar, y bar. X bar, y bar is going to be for the whole plate. X tilde, y tilde is just for for a particular strip. Okay, so the moment's mass and center of mass of a thin plate covering a region in the xy plane. You're going to have, what's going to be different now is you're going to have a moment about the x-axis, a moment about the y, and a moment about the y-axis. And because you're going to be getting an x and y coordinate. Now the mass itself, you're just going to have one calculation for the mass, but the center of mass is going to have an x and y coordinate. Now when I was first learning this, it always kind of messed me up. It never made sense to me that the moment about the x-axis has a y in it. But the reason, remember, the moment is the distance times the mass, right? The moment is the distance you are from the center of the thing times the mass. Well, the distance you are from the x-axis is going to be y tilde, right? That's this distance right here is going to be y tilde. And the moment, so the moment about the x has a y tilde in it. That's why it's right here, y tilde. And then the moment about the y has an x tilde in it. And that's because the distance you are from the y-axis is an x distance. So it feels weird that you have those in there, but you do. Okay, and then this dm it has to do with the area, which you calculate that by taking the density and multiplying it by the area. And remember, your area is, in this case, it's just going to be length times width, where the width of your strip is either dx if you have a vertical strip or dy if you have a horizontal strip. Okay, so let's see. To evaluate these integrals, we picture the plate in the coordinate plane and sketch a strip of mass parallel to one of the coordinate axes. We then express the strip's mass, dm, and the coordinates, x tilde, y tilde. This is not, I think it moved to a different classroom.
110?
This is 110, but I think the class moved to a different classroom. You can check in the University Center. Okay, so we then express the strip's mass, dm, and the coordinates, x tilde, y tilde, of the strip's center of mass in terms of x or y, and then we integrate to determine the plate's location in the plane. Okay, so I'm ready to go and try a problem, and hopefully this will make more sense. All right, so you are asked on this problem to find the center of mass of a thin plate of constant density covering the given regions. That's what we're going to do on these two problems. And this first one is the region bounded by the parabola y equals x squared and the line y equals 4. So just to get sort of a visual of what you're looking at here, what you're thinking about. Y equals x squared, of course, is just the parabola. And y equals 4 is just a horizontal line. And so, of course, your points of intersection, if you just set x squared equal to 4, you should see that your points of intersection are negative 2, 0, and 2, 0. I mean, negative 2, 4, and 2, 4. So here's 2, 4, and here's negative 2, 4. And you should probably feel that your x coordinate of the center, you may already sort of be able to tell me where, since you know that it has constant density, you should already be able to tell me where the...
Is this 110?
This is not, this is 110, but your class has been moved. Can you please check in the University Center?
Check with who?
Just down the hall in the University Center.
You ought to put a sign on your door.
I know. I guess I could stop the recording and put a sign out. You know, or... All right. Hold on. How much time do I have? All right, let me stop.